Welcome and thank you for joining today's webinar with co-founder and CTO of InGuardians, Jay Beale, in an awesome webinar topic today, you guys, securing applications with Linux containers. You're also joined by BeyondTrust security engineer David Grendis, who will run us through an overview and demo of PowerBroker for Unix and Linux after Jay's presentation, so please stick around for that portion. My name is Sarah, your webinar host today. A kind reminder to please submit your questions via the GoToMeeting console anytime throughout the webinar, and we'll cover your questions at the end during our Q&A time. So anytime you have a question, just pop it on in, and I will be monitoring those throughout. Also, today's session is being recorded. You'll receive a follow-up email containing links to the recording and the slides shown here today within 1 to 2 business days from now. So at this point, let's hand it on over to Jay, who will jump right in. Welcome aboard, Jay. Take it away.
Hi, I'm glad to be here, and I want to give a big thank you to BeyondTrust for sponsoring today's training. I'm going to talk to you about securing applications with Linux containers. So let's get right into it. So here's my bio slide. It's just like all bio slides, it's a sea of text, so I've created another bio slide, which is my graphical bio slide. So let me know afterwards. Feel free to tweet me and let me know what you thought of this one. Okay, so here's what we're going to do today. So we're going to talk about Linux containers, what they are. We're going to create a Docker compatible container. We're going to look at the security features that Linux containers bring, and then we'll look at some free tools that make those security features easier. And then finally, we'll hear from BeyondTrust about PowerBroker for Linux. So with that said, let's get right into it. So Linux containers have been around a long time. It feels like they've only been here for 5 years since Docker and Kubernetes popularized them, but they've been here since 2005, and they got started, as we'll talk about later, as a means for getting a whole bunch of work or a whole bunch of programs onto a system, potentially in a multi-tenant environment where you have different people, different clients bringing those workloads. So we're going to talk about this, but let's start out with just talking about what a container is. So a Linux container is we think of it as a kind of lightweight virtual machine, and it uses two features, and it uses two features, and one's called namespaces, the other's called control groups, and we'll get into this, but basically the biggest one that people notice when you start up a container is that the namespace basically does a lot of what we think of virtual machines as doing, and it provides, you take a program or multiple programs, you put them in a container, and that program gets a different view of a bunch of the vital resources, like the file system or the network interfaces, and I'll go through that a little bit more on the next slide. And then control groups put some resource limits on what that container or what those contained processes can use on the system. So the namespaces part of it means that you have that each, and the cool thing about containers is that you could use only some of these and not all of them. In general, you use almost all of them. But the programs that are in a container, they'll get, first with the mount namespace, they'll get a different view of the file system. And that's something where actually, if you're old school Unix and Linux like me, you're used to change roots or chroots, where your program saw a subset of the file system, some subdirectory was its root. This is similar to that, except you get to define a completely separate file system, and we're going to talk about that a whole bunch. You also get a container can have a different view of the network. It can have additional and different network interfaces. It can have more network interfaces than the host has. It can have obviously different IP addresses and a different routing table. It gets UTS. It gets different host names, a different host name and domain name from the main system, or from what we call the host system. It gets a different view of the process ID space. So if you do a PS listing in a container, you get a subset of the processes that are running on the host, just the ones that belong in your container. You get different inter-process communication, and optionally in Docker, this isn't the default behavior, but we're going to see how to do this later, you can have a different set of users from the main system. So the control groups is just on setting resource utilization limits, and you can do that in there are a pile of different ways. I have I'll be doing a blog post for this webinar, and it'll list out all the different control groups that are there. These two things, the control groups part of this basically got brought to bear most of all originally because this whole technology was basically meant for multi-tenancy. It was, I have a machine, and instead of and I want to operate like a platform as a service. I want to, instead of giving each of my customers who are going to use that, who are going to share that machine, their own virtual machine, I want to be able to pack a lot more of these kind of virtual machines or containers onto a system than I normally could with virtual machines, and that's where this thing came from. To give you a sense, containers are so lightweight compared to virtual machines that I actually run Docker on a Raspberry Pi, on a Raspberry Pi 2, and I can get a few containers going at the same time, and you can't really get a hypervisor onto a Pi. So let's keep going. So containers versus virtual machines. In the case of a virtual machine, you're simulating, for each virtual machine, you're simulating an entire, you're simulating every bit of the hardware, and you're giving each virtual machine its own kernel, and you're giving it all of those core subsystems of an operating system, like the system logging or the cron daemon or so on. With containers, you generally don't have a duplicate kernel. They're all running on the same one kernel. They're not getting separate simulations of all the hardware. And honestly, they generally don't get any of those redundant processes. You don't have a separate logging daemon in each container. You don't have a separate cron daemon in each container. You can if you want to, but you don't have to. And so in practice, you don't. I'm going to keep going. I know we're going a little fast right now, but that's so that we get to demos and we get into the deeper stuff. So if you've never heard of a container runtime, Docker is a container runtime. That's the most popular one. But if you look into this a lot more, there are a whole bunch of container runtimes out there. While Ubuntu supports Docker, they have their own thing called LXD. You've also got CoreOS, which has created its version called Rocket or RKT. Docker's built off a version called Containerd, and there are a heck of a lot more out there. We're going to use Docker basically because it's really popular, and so it's very easy to get started with. It's also really fun, and I hope as we're going through this, you'll kind of get some of my enthusiasm, because I sure as heck really enjoy containers, and Docker introduced me to them and made them a heck of a lot of fun. As much as I'm going to tell you about my fun, I'll also tell you about the fun of doing security with them. So we're going to use Docker, and you can use Docker, and then you can export that Docker container, and you can launch it with any of the other runtimes, including with a non-daemon program called runc, and we'll come to that. So let's start though and talk about how you get going with Docker, and then I'll start showing you how you'll get going with Docker. And I definitely encourage you to watch this, to go back and watch this webinar again with your own system that has Docker installed set up, and just follow along, because you're going to be blown away by how quick and easy it is to get going. I know a lot of people have been meaning to get into this, have been meaning to get into Docker or Linux containers, or Kubernetes for a while, and just don't, and I think most of us don't realize how easy it is to get in to start. So here we go. So first, a few terms. So containers are those lightweight virtual machines, those jails that Docker is helping create and facilitate, and that's the running instance. And then you've got what's called an image, and the image is the persistent state of a Docker container. It has basically the configuration and the file systems, and we're going to come on to, the next thing to understand about that is that the image is actually made up of, one image is actually made up of multiple images. It's kind of an odd way of looking at it, but you'll see as we get into a diagram soon. An image has one or more what we call union mounted file systems, and union-mounted file systems are really, really cool because normally in the Unix and Linux world, we're used to this idea that we mount one file or one device as the root partition, and then we mount another one as /home, and that then makes everything on the root partition invisible. In a union-mounted situation, you mount an image and then as root, and then you mount another image as root, and whatever's changed in that second image are the only things that overwrite. So it's similar to a copy on write situation. It only overrules whatever files or whatever file changes it brings. The other thing we're going to come to is, and you'll see this in the diagram shortly, is that when you're looking at an image that has these union-mounted file systems, only the top layer, only the top one of those file systems is read-write, and that ends up being really powerful. So let's look at this in practice. We're going to be doing this shortly, but basically, if you were to create a Docker file and you wanted to basically start creating some Docker images that you can launch containers from, you'll start out with something that's pre-made, like the CentOS 7 image that Docker ships, and they ship it by way of blessing it from Red Hat. So you've got the CentOS 7 image. We can pull that down, and for our next step, we can take that and we can run a yum update command. And now you've got a union-mounted file system of these two images. The bottom image is read only. The top image is currently read-write. Now, if we do something else, that middle one, number 2, becomes read-only. And say if we install an Apache server, an Apache web server, that's now the read-write image. Okay, so now we've got an image. And now we could do one more step, and that is we could install our application and maybe mod security on that. And that gets us to the first thing we're going to launch a container from. But while we're at it, and please forgive my my silly animation, but while we're at it, we could then create an Apache. We could take that item 3, and we could launch another container from it and install Apache and install a second Apache application on it, running in Apache. And now 4 and 5 will be our 2 containers, and we could even go back all the way to step 2 and add an Oracle database. And it's going to be cool when you see how this works in practice. Again, my silly animations. So at this point, this is enough for the slides. We're going to come back to them in a little bit, but what I want to do is switch over to demonstration. And as in any of my other Beyond Trust webinars, I like to pre-record all my demos, even if that means I do it a few times, and then I edit them harshly and pull out vital seconds to make things move a little more quickly, and honestly to hide my typos. And I pre-record all those demos because the demo gods are just evil and tricksters, and I don't like them very much. So here we go. Let's see how fast you can get going with Docker. If you've installed Docker on your machine, here's a quick command: Docker run IT for interactive terminal. Then I say CentOS 7, and I say that's the image I want to start from, and then I say I'd like to use bin bash. And if I don't have a CentOS 7 image on my machine, it'll get pulled down from Docker Hub or from another repository that I've got set up, and this will come down across the internet. It'll get pulled down, and the cool thing is that any other time that I start a CentOS 7 system up now, it's going to be a heck of a lot faster because I've got that image already pulled down. It doesn't take up a lot of space. So now I've got my CentOS 7 image, and I'm inside the container. You'll see that I went from root at victim, which is what my host is, one of my favorite victim hosts, to the container, and this container's name is this long hex string that starts with ED. And if I run a PS command, I find that process ID 1 is my bash shell, and I've run ps-ef, and now I can, so that's my container. It has only one process in it, and then whatever that process starts. So now I'll hit Control PQ, and that brings me back out to my host. My container is still running, and I can take a look at it. I can run a Docker PS, and it shows me all my containers that are running, and I see that ED on the left, and that's my container's ID. I've got that it was from CentOS 7. It was created 13 seconds ago, and it's got a name of Admiring Mahariva, When you start up Docker containers, if you don't give them explicit names, their Docker just basically picks an adjective from its list and generally a famous person's last name from its list, puts them together randomly and says, okay, well, that's what your container is called. And it's kind of neat. There's a whole bunch of command completion stuff. So I'm going to attach back to that admiring Mahariva, and that just puts me right back into this thing that I control PQ'd out of. And I'm going to make a file system change. I'm going to go and create a file called foo and put J in it. And then I'm going to start up another container. And I'm going to start up another container starting from that same image. So Docker run -IT for an active terminal. I'll use CentOS 7, and I'll also run a bash shell in there. So I've got my second container. Look at how fast these containers launch. This is not like booting a VM. There's no foo file. Okay, I haven't changed my base image, and I'll go and create a new foo file here. I'll put in Node.js here, and now if I do a Docker PS, I see I've got two containers running. One's Jolly Boyd and one's admiring Mahariva, and I can look at each one of these, and I can look at what the foo file looks like. That Jolly Boyd has Node.js here, and I can exit that one, and then I can attach into admiring Mahariva, and I look at foo, and there's J. So these two differ only in that one thing. And now I want to show you, I've done my Docker images. We don't see anything separate from the normal CentOS 7 because I haven't committed, I haven't saved the read-write layer, the top layer of each of those containers. So now what I'm going to do is I'm going to commit them. I'm going to take that top layer and I'm going to save it. So I say Docker commit, and I'm admiring Mahariva, and then I tag it with something. So I'll call this one foo is J, and I get the SHA-SUM, and now I'll do a commit on Jolly Boyd, and I'll say foo isn't J. So now I'm going to have two more images. So if I run my Docker images command, I've got foo is J and foo isn't J. Unless these things are repos. A lot of this, you're going to notice as you look at a lot of it looks and sounds a lot like GitHub or Git, and that's intentional, and it's pretty darn neat. So here's something I just blazed past for a second was notice that foo is J, foo isn't J, and the original CentOS 7 are all the same size, 195 megabytes. So let's actually look at that. So if I run Docker images, I can run Docker history. Tell me the history of an image. And I'll look at the history of foo is J, and I'll look at the history of foo isn't J. And what I'm going to find is that they both start with the CentOS 7 image, that 2D one that you might remember that before if you remember Hex the way I do. But they then add one more layer, and that one layer in the one case is 40 bytes on foo is J. And on the other layer, it's 57 bytes on foo isn't J. And my guess is the difference in those two isn't just the size of that one file I created, but also the size of my shell history file. So the cool thing about this is that I have my CentOS 7 base system, base image, and then I have these other two images for these that I've created for these two containers, and the three of them together are 195 megs plus 40 bytes plus 57 bytes. And I can keep spinning up containers, and I'm going to use so little disk space, and I'm going to use so little CPU, and that just makes this really fun for deving code. So there's another cool thing, and I just ran docker inspect on one of the containers, and I get back this JSON structure. And this is another thing where you can start to see how these things were built for being orchestrated, and they're built for being inspected by other programs. Is that you can say, I've got a container, okay, container, tell me everything about you, and it gives you machine parsable JSON. And that, to me, is really, really neat. So let's go on to our next thing. I'm going to talk about how you build containers. You've just watched me build them, but Docker also has something called a Docker file, and it works like a make file, and you can see it's kind of capitalized like a make file. And a Docker file says, here's how you build an image. You start from this image name, and we're going to choose CentOS 7. We could have chosen, foo is J if we wanted. And then you run this command, and then you expose this port. You make port 80 available, and that's the only port that'll be available. And then you run this command inside the container. And then we can build an image from this. And the weird thing about building the image is every single one of these steps is going to result in another layer, another image layer, and those image layers get cached. So this step, I'm going to fast forward, another really good thing about recording your demos. So I'm going to fast forward all the way a good minute forward. This took about a minute from 4:11 to 5:11. And here's my image finishing. And what you see is that for every single thing that happened, Docker build basically created a container. It saved the layer, the changes in essence that happened from before running that command, that yum install or the expose command or what have you. And then it destroys the previous container, it starts up a new one, and it keeps doing that. And the nice thing is that builds up this cache. So the cool thing about that cache is that now, if I want to do that again, if I want to build another image, Docker build, I'll give it a tag. This one, previous one was my image. This one will be my image 2. And that went so fast that I forgot to pause it. So let's watch. So I run that Docker build -t my image 2 period, where to find the Docker file. And because we're able to use the cache, the whole thing's done that fast. So we can spin up more and more of these really, really quickly. So now I've got my images and I've got my image. So let's run one. Let's run that image, the first image we just created. So run -d for daemon mode or background. We give it a name, my container. We say what image to start from. And we've got that image running. And we can look at its logs. So we type docker logs my container, and we see basically the output of the Apache web server when it gets started. And now we can actually enter into the container. So even though there's a program running in there, let's go enter into it and take a look at it. So we run docker exec IT for interactive terminal, my container, and we're going to add a bash shell to it. So now there's a bash shell along with whatever was in there. And again, I've chopped my demo for convenience so much that we'd have to rewind it here and there. But so you're seeing I've got the Apache web server that started. The first one starts as root, then the rest of them start as Apache. Then I've got my shell that I just added in, and I've got my PS. So I can go into a container and I can add more processes, and I can inspect it and play with it. So let's now see what I'm actually getting out of this. Let's start up another one. And this time we'll run with that -d for daemon mode, and we're going to tell it not only is it exposing port 80, but we want to have port 80 get mapped to port 8123 on the host. And so we're starting up our web server, which is starting up another one of these. You're going to notice there are tons of containers, and I'm not even killing them all off because they're barely using any resources. So I'm going to run that, and the container itself, when I run docker inspect, is on 172.17.03, but what I've just told it to do with that run command was was to translate the host's port 8123 on victim to port 80 on the container. And so we're going to go to the host's IP address, which ends in 139, and we'll say port 8123. And again, I've been just really brutal in the way that I've edited this video. But you find that I get to the web server that's running in the container, and victim is an Ubuntu system, and this is the web server for a CentOS system because my container was CentOS. That's another cool thing. Back in the day, writing Bastille Linux, I used to have to work with so many different Linux distributions, and so I had virtual machines for all of them, and it was such a pain in the butt. And here we are with containers. I so wish I had it back then, because nowadays in my lab I've got Docker running, and I've got a ton of different distributions that are already pulled down and ready to go. So I'm going to switch back to the slides for a moment, and then we'll go back to demo. So I've just shown you how to use Docker, and you can get going. And now what I want to do is show you the security features that I've promised. And these are, the point of this for me is I got into Docker and containers not because I wanted to be yet another Docker fanboy, as it were, or have a lot of fun developing, or have this lab like I've been showing you, but rather because similar but far better than the roots we used to build in Linux hardening, for breaking exploits, for hardening applications to break exploits. Containers have brought some new features, like all these namespaces, and they've also made some existing Linux security features a heck of a lot easier to use and more accessible if you're not the one writing the program. And so these are the ones we're going to talk about, and we'll get into each one of these. So the first one we'll talk about is root capabilities, and this is an easy one, and it's a really powerful one. So the deal is, we're used to this idea that on Linux and Unix, it's really pretty all or nothing. You've either got a normal user, and that normal user has basically, has files they own that aren't owned by anybody else, but they don't really have any kind of special powers. You don't have different levels of admin. All of your different levels of admin are things you do with root privilege, whether you're using sudo or su or all the different tools out there. Power Broker will come up later, but all of your ability to admin the system come out of interacting with things that are running as root or using tools that let you run as root. So root has some special powers. The first one is the normal thing that everybody has. It owns a ton of files in the file system. But the rest of the powers of root come out of these root capabilities, the magic powers. And the POSIX standard actually goes and splits those out and says, okay, well, why don't we name all those so that you could choose to only have certain capabilities. And so there are a bunch of them named. If you read the man page, you'll see what all the different Linux kernel capabilities are, but here are 3 I've chosen just to highlight what they are. So the one that lets you read or write to any file, whether you own it or have permissions or not, is called DAC override, for discretionary access control system override. And then the one that lets you bind to a port below 1024 is called net bind service. And spoiler alert, this is the only one that most programs that run as root are actually running as root to get. Our Apache web server basically just needs to bind to a low port like port 80, and then otherwise it can be running as user Apache. It can run as a non-root user. So the cool thing is Docker by default already drops almost all the root capabilities except for this list, and it has to, because if it doesn't, it's too easy to break out of the container. But we can go further, and we can basically choose to drop all the capabilities except for the ones that our program needs, and it's pretty easy to figure out what your program needs. So I'm going to demo this real quick and go back to our recording. So I'm going to start up a container, and I want you to imagine in this container that there was a program that was running. It was listening to a low-numbered port, so it needed this one root capability. But that's why it was running as root. And an attacker exploits that program. There's a known vulnerability in it, or they found a vulnerability in it, and they exploit it. And that would normally give them a root shell. And so what I want to do is simulate what that root shell would look like. So here we go. Here's that root shell, except this time we're going to take away all of root special powers except for the ability to bind to a low-numbered port. And now let's test that out. So you're the attacker, you're on ID, you're like, oh, cool, I'm root. And now you're like, okay, I'm going to change the ownership of root's home directory. I'm going to do something that only root could do. And you get, nope, sorry, you can't do that, because we've taken away that root capability along with all the others except for this net bind service. So to me, that's just really, really neat. So that's capability dropping. The next is that, and I'm gonna demo this for you, but there's a privilege escalation. I work at InGuardians. We are primarily red teamers and penetration testers by trade, and so we're often, one of the things that we use in our field is called the privilege escalation, or the privesc. And if you land on a Linux system and Docker's running and you're not root, but the user you have is in the Docker group, then you can do this. You can basically say, I want to spin up a virtual machine. I'm gonna mount /etc from the host into a directory on the in the container, and then I'm going to do whatever I want to it since I'll be root there. And I've got a slide on. I've got a part of the demo on that. So I'm switching user to J in my demo, and I run that same command, docker run interactive terminal volume mount etc into /root on CentOS 7, and then I'll cat out etc shadow, something I shouldn't be able to do. And now I've got the shadow file from the host. That's not a very useful shadow file in this case, but I needed something simple. I could have modified the password file to change user J to UID 0 if I wanted to. So it's a cool little feature. What we can do to defeat that, and the reason I brought that privilege escalation up, is that we can actually say, okay, you know what, we're just going to remap all of the users in the container to non-privileged users, to non-UID 0 users, and honestly to users that don't exist in the host. And so it's actually really easy to do in Docker. So we create a Docker root user, and some distros do that by default. And then we go and set this, user NS remap, user namespace remap in the Docker in Docker's daemon.json file. And we create a set of user IDs and group IDs for Docker to use. And what this says is 30,000 is the first UID. That'll be UID 0. So 30,000 on the host will be UID 0 in the container. And then we'll use 65,536 more total UIDs. Do the same thing for GIDs. When we restart Docker, we're going to find that we can't do that. Well, first we can't see the, and I'm going to fast forward a little bit here. So when we do this, when we restart Docker, we won't be able to see our old images, but we will be able to basically create new ones, and they'll be under this new user ID. That's the one side effect. So you kind of do this on a system that you haven't been using a whole bunch. But once you do this, our little privesc won't work. So let's try our same command, and now we can't read /root/shadow because even though we're root in the container doesn't mean anything outside of the container. It's a normal user. So that's my other big demo. I'm going to go through a couple more features and a couple programs to make those features easier to use. So we've got the next biggie is syscall filtering, system call filtering with seccomp. Seccomp is maintained by Keys Cook at Google. It's really neat, and basically I should probably say what system calls are. So many of the things that a program does need the kernel to mediate for it. And that's even simple stuff like if you want to open a file or read or write to a file, you have to have the kernel do that for you. And the way you do that is you issue a system call. And that's your interaction with the kernel. You issue a system call called open to open a file, and read to read from the file, and write to the file, and so on. So it turns out that's really useful to filter what syscalls a program can have, and you can do that at the container level. And it's useful for two reasons. The one is you could profile the program and figure out what it normally does, and then restrict it to only do what it normally does. And the other is that you reduce the attack surface in the kernel. You make it so that if someone comes out with the next next copy and write vulnerability, they come out with the next kernel level vulnerability. If the kernel level vulnerability accesses the kernel via a syscall that you've blocked, then even though your kernel's vulnerable, you don't get hit by it. And that's what I'm all about actually in hardening. This is basically what everything that I teach at Black Hat and other places and in these webinars is all about. I'm trying to break exploits. I'm trying to break what attackers are doing. And so reducing a kernel's attack surface, that works too. So both of these are going to break exploits, are going to break exploits. So syscall filtering, it's a little tricky. It's gotten easier and easier, and I'm going to show you a tool that makes it even easier, but here's the basic process. You start out by running strace, which shows you all the system calls the program uses, and it does that in real time as the program runs. You exercise the program, and that gives you a list of syscalls, and you build a JSON file that expresses that list of syscalls. And then you start a container, and you add a security option to your Docker run command that says, hey, get a seccomp from this file. And then Well, invariably, if the container or the program in it won't start, you look at the log messages in the kernel audit log and figure out which syscalls failed, which ones you have to add. And you add those into your JSON file, and then you do that a couple more times until you've got the whole syscall filter right. And at that point, I like to say that's the point where you should publish that file to help other people out, so they don't have to go through that same profiling process. I'm going to come back to a way to make that profiling process easier, but I want to talk about it. I want to talk about the next security feature, and that is AppArmor and SE Linux. These are the mandatory access control systems. And you can use AppArmor or SE Linux for a container, even if you're not using them on the host operating system at all. It's actually really, really neat. On the SE Linux side, the way that Red Hat sets up containers to run is whenever you start a container, it gets an SE Linux label that makes it so that it can only read its own files, its own image, and it can't read any of the other container images, and it can't read the rest of the file system either. And that is just really, it's just really tight. It's basically adding another layer. AppArmor, I teach both AppArmor and SE Linux in my trainings, but AppArmor is hands down my favorite because you can get into it really easily and quickly. And if you look at my Beyond Trust webinar from November 2017, the link is in these slides here. You can learn how to use AppArmor and create an AppArmor profile. So all of this works with containers. The thing that I like, this is the last part of what we're doing here, is there are a couple tools that make seccomp a whole bunch easier, and AppArmor as well in the case of Docker Slim. And these are Docker Slim and FireJail. So Docker Slim is meant, its kind of primary purpose is to take a container and make it smaller. So you started out with that 158 megabyte image that we were dealing with for CentOS 7, and you set it up to do something, and so then you can basically give it to Docker Slim, and Docker Slim will launch the container, watch the application. You can use the application, or you can let its built-in HTTP probe do it, and it'll build up a list of file accesses and syscalls. And then it creates a new version of the image that's slimmed down that has only the files in it that your program actually used or needed. And it'll also build up a seccomp filter, that thing we were just doing with our 6-step process. And it'll build an AppArmor profile that you can use. And one of the things I like to do is basically say, okay, well, I want to leave the slimmed down image behind. I didn't really need that, but I will take the seccomp and AppArmor profiles and use that for the original image that I ran the Slim on. Docker Slim doesn't permanently modify your image; it gives you a new image. So, time permitting, and I think we do. Yeah, I'll do a quick view of the demo. This is, and I'm running. I run my vulnerable container, which is a PHP application, and this PHP application is one I've coded, made it so that if you pass it the get argument evil equals 1, it shows you the etc password file, or it runs a command. So here's my vulnerable one. So now what I do is I profile the application, and that is I tell Docker Slim to go and watch it and build up a. You see the bottom 2 lines. It builds up a seccomp filter and an AppArmor profile, and then I go and I run it again. And here's my before, where evil equals 1 gets me a etc password file. Here's my after, it's pretty darn powerful. The other tool, and this is the last thing I'm talking about today, is FireJail. And FireJail, Docker Slim actually used a Docker image and was building something for Docker. FireJail is a different purpose. And honestly, it's geared toward GUI applications more than servers, although I found you can use it for servers as well. And what it does is it builds its own Linux container. So it's not building a Docker container, and it builds it on the fly. It's not working with a persistent image. And it's building that container using those same namespaces we've been using. And it can use seccomp, and it can use root capability dropping. And it comes with a whole bunch of profiles. It doesn't profile the application for you, but the authors and the other people working on the project have built a ton of profiles for applications so that you can run your BitTorrent client, or your music player, or your browser, within FireJail and have something and have this thing so that if it is compromised, it can't go and serve up files from your file system. And people are really excited about that for defeating some of the vulnerable plugins and so on. It does have a default server profile, and then you can build out the profile further, and it's pretty easy to use, and I'm really impressed by it. So last thing I want to say, the next step for me here. We've been using Docker a whole bunch, and people often will say to me, "Well, wait, you're building a container with Docker, but Docker's adding attack surface, because now what if there's a vulnerability in the Docker daemon itself?" And so that's where what I'll say is you can take that container that you built with Docker. So build a container with Docker because it's really easy and it's great for prototyping, and then run it with runc, which is not a daemon. It is just a command line program. It's originally created by Docker and lets you run that container without the daemon running. So anyway, that's the end of my slides, and at this point now I want to turn it over for a word from our sponsor. Dave from Beyond Trust is going to talk about PowerBroker for Linux. So thanks a lot, Beyond Trust. Hi, Dave.
Hello, thank you. Fabulous, by the way. What I wanted to do was sort of put a pause sort of right there at the end of Jay's demo, and I wanted to explain a little bit about PowerBroker for Unix and Linux and how it can help, and then even tie it back into some of what we saw today. So I guess to begin, I wanted to first highlight where we're going to focus, which is right here under Server Privilege Management as it relates to Unix and Linux. At Beyond Trust, we do much more than that. You can see that we've got areas of endpoint privilege management as well as enterprise password security. So we're not just a one-trick pony here. You'll see that we've got you covered front to back. But when we're looking at just privilege management, that's the idea of logging onto a host as a named account and being able to execute or run various commands as root, as we were just talking about, where you're either a normal user or you're root. Well, in this case, we're going to allow you to be something in between, really a least privileged or a purpose-built type of account. This will allow you, of course, to do things such as eliminate this whole idea or concept of needing to share these privileged accounts amongst people, creating the ability not to be able to know who's done what, where, and when. So what we'll do is we'll allow the ability to, of course, track who's run these commands, Docker space and whatever command that might be. Log this, as well as audit it, meaning we won't just log it as an event, who's run what commands, where, and when. We'll see what they've done with these commands. And we can extend this not just at the command level, but all the way down to the system level controls, meaning, maybe I am root, but I want to only allow you to execute or certain binaries and not others. Or even at the file system level, we don't want you to be able to modify the etc directory, but you need to go over to the var logs and examine them. Those are the types of things we can do with our ACA. And of course, this can extend not just to your Linux operating system, but we can help on the routers and the firewalls as well. I mentioned ACA, and that stands for Advanced Control and Audit. Some of the capabilities here, and maybe we've got some people in the audience that have been familiar with PowerBroker, Unix, and Linux in the past. Well, in the last year or two, that's where ACA has really come along, and we've always been asked, well, what happens if someone executes a script as root? Or they somehow get nefarious code within a script that's being executed, and my user has the ability to run these as root, these scripts. Well, that's where ACA can come along and allow you to audit activities, not just that the person used when they typed, pb run space in some command. If that command was a script, we'll audit what was in the script. And in fact, if there was something nefarious in that script that user wasn't authorized to do, that can be blocked. So this will create that tamper-proof trail, audit trail along the way. And finally, this is my last slide before we jump on in and look at about a 10-minute demo. How does it work? There's a little bit more, but there's three primary components to PowerBroker, Unix, and Linux. There's pbrun, that's the client. There's pbmasterd, that's the policy server. And then there's pblocald, that's essentially the agent that executes the commands as the run user. 9 times out of 10 root. Could be Oracle, could be anyone. So essentially, though, what happens is when the user logs onto a system and they need to elevate, they would type pbrun space, and then, of course, their command or command sets. This gets sent over to the policy server where we evaluate it. This is where it's now logged, creating an indelible audit trail. We're not giving the user root access directly on the system where the policies are being stored. Policies out here on a separate server or sets of servers for high availability. So now we also have that event indelibly logged out on this server. And assuming that the user is authorized to run said command, the policy server instructs the agent to run this command, at which point we can, based on your policy, initiate an IO log, where we'll capture not only the input that we're giving or the script's giving or the user's entering through PowerBroker, but also the output. So all of this now gets indelibly logged, and at no point have we given the user root access to a system where the policy is being held or where any of the audit trails being held. And of course, we can pass all of this insight up to our GUI, graphical user interface beyond insight, for additional reporting and analytics along the way. That pretty much wraps up the actual demonstration, the actual slide portion of the demonstration. What I wanted to do next was show it in action. So I'm going to quickly switch over to my Windows host. I'll bring up my terminal where I'm logged on to Lin 7 and Lin 2 as my user, C. Swanson, or Carrie. We can see we're C. Swanson on both of these. By the way, you'll note we are part of the domain users. Yes, this is an Active Directory-based user. That's where our PowerBroker identity services can come into play. If you're looking for an AD based or joining your Unix and Linux host to AD, there's lots of advantages to that. But at the end of the day, PowerBroker Unix and Linux doesn't care. As long as you're a valid Unix Linux user, you'll be able to elevate using PB run. So, for example, I'll do PB, well, before we do that, let's just do Docker, which is installed out here on Lin 7. And you can see there's numerous options we have there. And if I try something like Docker ps-a, we saw Jay do some of that in his demo. And that's listing out or attempting to enumerate my various containers. I can't do any of this if I'm not root. So that's where we will do something like PB run show, allowing Carrie to list out the various rule sets that apply to her. And one thing to note, I've actually created some very purpose-built restricted commands for Carrie, and that's how we can avoid, in many cases, allowing Carrie to launch various images or containers in Docker or administer them in a way that we don't want her to. We can now not only control, yeah, Carrie, you can run Docker as root, but I can now control the arguments that Carrie can run. So for example, if I do a PB run, probably should have had a few more fancier ones than show, but we're okay here. Docker show. This will go out and execute the various commands. So Docker space ps-a, showing me which containers I have out here and their friendly naming conventions. Maybe I want to restart one. You can see this guy looks like about an hour ago was the last time it seemed to have been touched. I'll do a Docker, we're going to need to elevate, of course, PB run, Docker dash restart. Identify my container ID, pop that in there, and go ahead and paste it in. And you'll see we'll reach out now. We'll restart that particular Docker container. And if we look from this side, you can see now where it was about an hour ago, it's about five seconds ago is when it's been touched. So that's the idea of allowing you to create a very defined list of commands and limiting what users can do. Sure, we can have some people, maybe they can come in and grab a bash shell and do everything, and we just want to IO log it. So depending on where you need to be, that's where granularity-wise, depending on where you need to be granularity-wise, we've got you covered. And all of those events right there, both IO can be IO logged as well as event logged, and we can view them and analyze them. What I'd like to do next is quickly jump over to Lin 2, where we're still logged on as Carrie. We'll do that same PB run show. Keeping in mind, too, all this policy, by the way, is still administered centrally. It was one of the slides I kind of skipped over. But what we're bringing to the table is this whole concept of centralized policy management and centralized auditing and logging. So you have one place where you would make these changes. To show that remote command execution example I was talking about, we can do a PB run -h, and this could be built into my policy file, Lin 7, and I want to do the docker-show command. So now you can see I can create yet, that's not going to work, is it? EOC. Something like that. We'll reach out and show this. So this gets back to that whole concept that I was talking about. We have PB run and we have the agent. And we have the concept of run hosts where we would run the command on and submit hosts where they're submitted from. So you can see I can create another layer keeping Carrie off that host but still being able to do her job or administer Docker in such a way. So that extends, of course, not just to Docker, but any type of application or even basic system administration. A very common one we see is, that scripts issue I was talking about, where we can maybe descend into my scripts directory, take a look. These are obviously owned by root. Carrie's not, but we'll do a quick PB run because she knows she can and grab an entire bash shell as root. I've told her that we're going to IO log this. It's up to you if that makes sense or not. And now we can go in and do a quick vi into this particular script. See what was going on. Lots of changes or people trying to make changes, but you can see within this script, it goes out and reboots the system. Additionally, it cats my shadow and password file. Maybe someone put that information in there I didn't want in there. Or maybe Carrie, in this case, wants to, again, add some more bad things to the script and go ahead and save that. But you can't. And that's because she's not authorized to. She has exec rights over script1.sh even as root, but she does not have the ability to modify. And so based on her group membership, we don't need to CD, we'll go ahead and execute that, script1.sh, but based on her group membership or any users, some people can modify that script, others can't, or anything in that scripts directory. And clearly here we see that the server did not reboot. ID shutdown -R now, permission denied. So I've both at the file system level, I can say what binaries can Carrie execute as root and which ones can't she. And then we're going to audit all of this. So just to show you what I mean by that, I'm going to exit out of Carrie's bash session. We'll do a quick PB run show. Take a quick look. I've got some product controls up here. So let's see what we've got. Now this was all saved out on my logging host out on Lin 1. We're just going to look at it from Lin 2. Allow me to do a quick PB run list logs. Here are the various IO logs, and we do have a GUI around this as well that you can query these type of logs, but we'll grab the one that we just generated here as Carrie, quickly copy it, and I'll do a PB run replay to see what we've done. Paste that in there. So here's your your command line IO log. You can see all the mistakes I made in my typing. I went and tried to add some bad things to a script, tried to save it, couldn't execute it. So this is what you would get with your standard IO log, and I can backspace through them all if I want to see. The T key tells me the exact time when this was taking place. V actually will output a list of environmental variables that were in place while this was going. And find will actually allow me to search across this IO log for any particular texts that I might be looking for. That's what you get, and probably have had for some time if you're a Power Broker Unix and Linux user. But what we can also now bring to the table, not just that level of granularity, but also history, history. Same IO log, but now we can see, maybe at the command level, that the history, who's running what, right? So I don't have to step through with the space bar. I can see we entered into the scripts working directory. But you'll note here, this is actually where we were allowed and did in fact execute script1.sh. It's gone through. We blocked that reboot command. Further on down the line, I can see where Carrie also decided to, from her CLI, try and issue the reboot or shutdown now command. Those are all blocked. So this is going to give you that historic view of that same IO log, not only just from what Carrie typed, but also what took place within that history. Of course, we've got all of this can be viewed directly from where we are, or we can take a look. I was hoping I'd stay logged in. to what we call our Beyond Trust Server Management Console. This is this tool that we use for all of our Unix and Linux products to deploy them, to see what pieces are running on them, what components is it, here's my client, my policy server, my licensing server, and log server, and so on. All of that can be viewed here, and we can use this to upgrade systems, deploy, and so on, as well as even join them to Active Directory if you were looking at AD bridging. Policy management can be can be performed here, as well as taking a look at that same I/O log. You can see here we have that 1.5-minute I/O log that Carrie executed there on Lin 1, and we wanted to look at it from this view. We certainly can. So this was really just meant to be a quick teaser as to what PowerBroker Unix and Linux can bring to the table, whether it's with managing your Docker containers or just the total operating system there with the underlying host or any sort of database or Unix and Linux operating system. If you have any additional questions, please let us know. We're more than happy to run through a more purpose-built demo and answer your questions on a more private call. What I'm going to do now is turn this over back to our organizers, and we'll be able to put up a quick poll.
Yeah, so that's a perfect segue, Dave, because our poll, if you guys would like a more personalized one-on-one demo with a Beyond Trust Security expert engineer, if you select yes, we will schedule a call with you, have a conversation, and then actually personalize a demo for you. So you can get a little bit deeper into one of our PowerBroker products, PowerBroker for Unix, Linux, or even our Retina vulnerability management products based on your needs and your conversation. So I'm going to leave this up. I had a question come in, or a couple questions come in. Jay, so if you want to make sure you're off of mute, and this came in from Jin Mao. Is it possible to block a user in Docker group from mounting of the host? Is it possible to prevent user from mounting an NFS share to a container and switch his UID to another user in the container?
That's a really good question. Yeah, you certainly could. So I'm just going to go with yes. You certainly could. And that's a good question, because the NFS is another thing we've used as penetration testers, where you're saying, okay, well, if I can mount something, if I can be on my own machine and mount something from my target machine, that'll get me pretty far. And honestly, when you're using Docker, when you're using any of the container technologies, one of the biggest places where you have to be really careful with is making sure that the containers aren't mounting things from the host itself. NFS shares are the next level up, but the mistake a lot of people make is, as you saw with my volume mount, where I was mounting /etc onto /root. Those volume mounts are basically a way of kind of breaking the file system, almost breaking the file system namespace containment. So you have to be really careful there. Thanks.
Okay, closing the poll. Thanks to everybody who selected their answer. And Jay, would you recommend starting out with Docker on Red Hat-based systems or Debian-based systems like Ubuntu?
I would actually really recommend starting out. A lot of us, that's a really good question, because a lot of us are using things like Ubuntu or other Debian-based systems at home or in our hobby work. But then when we go to work, we're on Red Hat, we're on Red Hat Enterprise, or we're on CentOS or another variant of it like Oracle's Linux. And because of for a lot of reasons, partly just the amount that the Docker folks, that the Docker devs are clearly using Ubuntu or Debian-based systems, it's just a heck of a lot easier to start using this on Ubuntu and Debian, get your feet underneath you, and then bring it over, and then bring it over to Red Hat-based systems. So you'll have lots of fun. I do my training classes. When I'm doing my training classes, we do Docker and containers and Kubernetes using Red Hat-based systems. But if you're doing this at home, it's a heck of a lot easier to start with Ubuntu or Debian. Good question. Thank you.
Time for one more question. David, what controls are in PowerBroker for Unix and Linux to stop someone tampering with the logs, especially if they have been elevated to root? And make sure you're off of mute, David.
Thank you. We have two in this case. One is just the sheer architecture of the system, which I touched on, meaning that we don't ever, by design, we don't even give users any sort of elevation on the same container, both where the logs are being stored as well as where the policy is. Because let's face it, getting to the audit trail is one thing, but if you are able to manipulate policy in some way, that's also pretty key. So we don't ever allow them to. And then you saw with that whole concept of ACA, should you decide that, okay, well maybe it is going to be authorized for this one small subset of users, that's where we would start looking at ACA, Advanced Control and Audit, and actually specifying the various portions of the file system where even when you are root, if PowerBroker is granting you that rights, you will not have some level of access on at the file system level, like read, or certainly not delete or modify.
Okay, you guys, that wraps up questions. Thanks, everybody, for submitting your questions today. And a reminder that you will be receiving a follow-up email containing links to the recording and the slides shown here today within 1 to 2 business days from now, and it will come from communications@beyondtrust.com, so be on the lookout for that follow-up. Jay, thank you so much for being here today. What a fun webinar, and you covered a lot in your 40 minutes. So thank you so much for being with Beyond Trust today. We really appreciate you.
Well, thank you. I had fun. Thanks.
Thanks, everybody who joined, and we will see you guys at the next webinar. Take care, everybody, and goodbye.